Now that we solved this problem, we're going to make a project out of it. In this project, we investigate the most economical shape for a can. We first interpret this to mean that the volume V of a cylindrical can is given, and we need to find the height and radius that minimizes the cost of the metal to make the can. If we disregard any waste metal in this process, then the problem is minimizing surface area of a cylinder. In previous example, everything was nicely written and H became 2R. But if you go to a supermarket and use a ruler, you can basically see H divided by R. This ratio is not exactly 2. It varies from 2 up to 3.8. Why this happens? In the first question, the material for the cans is cut from sheets of metal. The cylindrical sides are formed by bending rectangles. These rectangles are cut from the sheet with little or no waste, but if the top and bottom discs are cut from squares of sides 2R, this leaves considerable waste metal, which may be recycled, but they are of no value to the maker. This is the case and show that the amount of metal used is minimized when the ratio of height and radius is 8/pi or about 2.55. Let's go over the solution together. The amount of metal used in making up each top or bottom is 2R to the second power, which is 4R squared. So the quantity we want to minimize is basically the surface area is 2 pi RH plus 2 times 4R squared. At the same time, we know the volume formula is pi R squared H. It means that H is volume divided by pi R squared. Substitute H in the surface area formula, and A, or the surface area, becomes 2 volume divided by R plus 8R squared. Now take the derivative with respect to R. The derivative of A with respect to R, dA dr, is equal to, here the derivative with respect to R, negative 2B divided by R squared and plus 16R. To find the critical value, set it equal to 0, and then you get 16R cubed equals to 2V, 2 times the volume, which is 2 pi R squared H, or H divided by R becomes 8/pi, or about 2.55. This gives it a minimum because the second derivative is positive, and the second derivative is positive, the graph behaves like this. It means that you have a minimum value.